Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to learn how to calculate the standard free energy change for any given chemical reaction. So let's start. The first thing that I do want to point out is the standard free energy or standard free energy change is represented by this delta G with this circle in the top right-hand corner. And so that circle represents this idea that the free energy change was measured under standard conditions. And so what are standard conditions? The standard conditions is 25 degrees Celsius, that would be the temperature, and at 1 atmospheric pressure. And so these standard conditions did not change from what you guys learned in the first semester of general chemistry. So hopefully you guys were exposed to standard conditions for enthalpy in the first semester of general chemistry. Basically, if the free energy change was measured under these conditions, then we can go ahead and represent the change in free energy as the standard free energy change. Now there's two ways to calculate the standard free energy change. First, we can go ahead and use this equation that we saw when we were talking about Gibbs free energy in the last lecture video. The only difference between this equation that I've written down and the other equations you guys saw in the previous lecture video is the presence of this knot. And so these circles, if you will, found on the top right corner of each letter of each thermodynamic quantity represents that it was measured under standard conditions. And once again, standard conditions is 25 degrees Celsius and 1 atmospheric pressure. Now, another way for you guys to calculate the change in standard free energy or the standard free energy change is going to be a modification of Hess's law. We've seen the modification, or we've seen Hess's law been modified for entropy, and we're also going to do it again for Gibbs free energy. And so the change in the standard free energy is going to equal to the sum of the number of moles multiplied by the change in standard free energy of formation of each of the products that's present, minus the standard free energy change of formation of the reactants. And so this is a somewhat of a new term for us in this lecture video. So let's go ahead and go over what this DeltaGF is. And so DeltaGF with a knot, it's basically representing the standard Gibbs free energy change of formation. And so the idea is, how much free energy was consumed or released for the formation of exactly 1 mole of product. So if you guys have this generic chemical reaction, let's just say that you have, let's just say that you wanted to produce exactly 1 mole of water, whether it's 1 mole of water in the solid state, gas state, liquid state. Each of those values will be a little bit different, but let's just say that you just want to produce 1 mole of water. And the only way for you to do so is to create it from its elemental state, kind of like Lego bricks, right? So if you wanted to build a castle, then you need to put all of the little elemental pieces of the Lego bricks together to form that castle. And so here we have 2 hydrogen atoms, and we also have 2 hydrogen atoms. And so we only need 1 mole of hydrogen gas. And since oxygen is naturally diatomic, then we only need one oxygen from this O2 gas, and we're going to represent that by writing 1/2 as the coefficient. And so when you add up the number of moles, the number of atoms, you get exactly 1 mole of product. And so the amount of free energy consumed or released for the formation of 1 mole of product is known as the standard Gibbs free energy of formation. So it's very similar to it's very similar to DeltaGF, so standard heat of formation. And in terms of units for the standard Gibbs free energy of formation, it's going to be in kilojoules per mole. Okay. And since we always want it in terms of a per mole basis because we're trying to create 1 mole of the product, it makes sense for the mole to be in the denominator. Now, let's go ahead and talk about the standard free energy change of formation for pure metals and diatomic elements. And that's something that we've kind of crossed when we're talking about the enthalpy of formation or the heat of formation and entropy as well. And so for pure metals, so for example, if you guys have a pure metal in your chemical reaction such that it's represented only by itself and the symbol solid, right? So magnesium solid, lithium solid, gold solid. The change in Gibbs free energy of formation under standard conditions is equal to 0 kilojoules per mole. And so the idea is, how much energy, or I'm sorry, how much energy will be, released or consumed, how much free energy will be released or consumed for the formation of these pure elemental substances. And the answer to that is 0, because they already naturally exist. So the same thought process holds for diatomic elements. So here we have H2O2 F2 Br2 I2 N2 Cl2. And so for your diatomic elements, since they are naturally occurring, the change in Gibbs free energy of formation under standard conditions, it's going to be 0 kilojoules per mole as well. And so the rule for diatomic elements and pure metals for the formation under Gibbs free energy is similar to that of the heat of formation for enthalpy. However, for entropy, each substance, regardless if it's a pure metal, a diatomic element, or a molecule or a compound, will have some type of entropic value. And so therefore, for pure metals and diatomic elements, the entropy of formation is going to be some value. Right? There is going to be some value that's associated to it. All right. So let's go ahead and go through this example just to demonstrate how we can use both of those equations. I'll flash it again. We'll see how we can use these equations to determine the change in standard Gibbs free energy. All right. So the first thing that you want to do is you want to check your balanced chemical equation, right? And so in this scenario, I went ahead and balanced the equation for you. But when you guys are doing this on your own, it never hurts to check if you have a balanced chemical equation. And so what we're going to do is we are going to calculate the change in standard Gibbs free energy. And in this scenario, we're already given the enthalpy value and the entropy value. And so it only makes sense for us to use the first equation, where the change in standard Gibbs free energy is equal to that of delta H naught minus T delta S naught. And so all we have to do in this scenario is just plug in our values. Now, when we plug in our values, we want to make sure that our units match. And so here, notice that I'll go ahead and highlight it. We have kilojoules for enthalpy, we have joules for entropy. And so you want to convert one to the other. For me, it's just easier to go from kilojoules to joules, just multiply it by 1,000. And so for the value that I'm going to plug in, for the value that I'm going to plug into this term, I'm just going to put in negative 246.1 times 10 to the positive 3 joules per mole. And so this scientific notation, that times 10 to the positive 3, that's equivalent to 1,000, right? And so I'm just taking that kilo out of there and representing it as times 10 to the positive 3, and that's going to be my prefix conversion. Notice that my units are now in joules. And so I'm going to go ahead and subtract that by temperature. Now, if you guys read the problem, it didn't tell us what the temperature is, right? It didn't tell us explicitly. But if you guys recall, this naught represents standard conditions. And standard conditions states that the reaction should be occurring at 25 degrees Celsius and at 1 atmospheric pressure. And so the only number that's relevant to us for this problem is at 25 degrees Celsius, because that's what we need for temperature. And so we need to convert this into Kelvin, just add 273.15, and that's going to give us 298.15 Kelvin. And so here I'm going to put 298.15 Kelvin, and then I'm going to substitute in the value for my entropy. In this case, it's going to be 377.1 joules mole Kelvin. Now, when you multiply the T and the S term, so this is going to be temperature, this is going to be delta T. Notice that the unit for Kelvin cancels out, allowing the joules per mole to match up very easily with the joules per mole as well. And so from here on out, it's just like multiplication and subtraction, really. And so there's nothing really fancy to this specific problem. So I'm just going to go ahead and multiply these two. So I'm going to go ahead and do the T delta S term first. So 298.15 times that by 377.1 joules. And so what I get here is going to be, and I'm reporting this in scientific notation, and since I'm doing multiplication, I need 4 sig figs in this case. And so 1.124 times 10 to the positive 5 joules per mole. And if I were to bring this down, this is going to be, 246.1 times 10 to the positive 3 joules per mole. And so just to make it clear, if I move this decimal if I move this decimal place 2 places to the left, this value is going to become times 10 to the positive 5. Okay. And so I can go ahead and resummarize as 2.461 times 10 to the positive 5 joules per mole. And so I'm just going to go ahead and carry this part down. Now, you guys don't need to convert it to the same magnitude. I just wanted you guys to see that you can move your decimal places to the left or to the right, just as long as you guys are reflecting that movement in your exponent in your scientific notation. All right, so the last thing that I'm going to do is just subtract these two. So here I have negative 2.461 times 10 to the positive 5 minus 1.124 times 10 to the positive 5. And so overall, the change in my standard Gibbs free energy value is going to be negative 3.585 times 10 to the positive 5 joules per mole. Now, if I wanted to express this value in terms of kilojoules per mole, I'm going to take this scientific notation and I'm just going to break it down into two pieces, times 10 to the positive 2 and times 10 to the positive 3 joules per mole. The reason why is because this times 10 to the positive 3 equals 1,000, which is a kilo. And so I can write my final answer as negative 3.585 times 10 to the positive 2 kilojoules per mole. Okay. And if I didn't want this scientific notation, I can go ahead and just expand this 2 places to the right. So this is going to be negative 358.5 kilojoules per mole. And so I show you these steps to demonstrate that there's many different ways to express your final answer. You just want to make sure that the final answer is correct and that it's, in the same magnitude as everything else. And so, for example, if you said the answer is going to be negative 358.5 joules per mole, then that answer is wrong because you're off by 3 orders of magnitude. So you just want to make sure that you represent every single part of the scientific notation, either as a prefix or you're expressing it by moving the decimal left or right, depending on the sign of the exponent. All right, and so this negative value is telling us that the forward reaction is going to be spontaneous. And so if these two reactions were to occur, if these two reactants were catalyzed in some form or manner, so maybe like a quick spark, producing a combustion reaction. So if you guys look at the products here, notice it's CO2 and H2O. And so this is an example of a combustion reaction. In addition, you guys have oxygen gas as one of your reactants. And so this negative value is telling us that this reaction will be spontaneous in the forward direction. And so why is it spontaneous in the forward direction? Because we're taking the difference between the products to the reactants. We're doing final minus initial. Now, if we're doing initial minus final, then we're talking about the reverse reaction. All right. So let's go ahead and take a look at this next example. Here we're going to calculate the standard free energy change for the following reaction. And so this is a chemical reaction that we've seen once before in a previous lecture video. So we have aluminum oxide that's being reduced with 3 moles of hydrogen gas to produce aluminum and water, water vapor specifically. And so if this is the question that I ask you on an exam, for instance, what would you do, right? I mean, this is the only piece of information that I give you on the exam. What would you do? Okay. Now, if you guys recall, the standard free energy change. And so, by the way, let me take a step back. This phrase right here, calculate the standard free energy change. Once you see that phrase or some variance of that phrase, that's referring to delta G naught. Okay. And so one way that we've learned how to calculate delta G naught is to look at the enthalpy values and subtract that by T times delta S under standard conditions. And so if this is the equation that we're going to be using to calculate the standard free energy change, then that means that we need some type of enthalpy value, and we need the entropy value, and we need temperature. So let's talk about temperature real quick. This temperature should already be known. Why? Because, once again, we're under standard conditions. And so under standard conditions, the temperature is going to be 25 degrees Celsius. And so we just convert that into Kelvin, and that's 298.15. And so we know one piece of information to calculate delta G, in which the temperature is 298.15. How would I calculate these two? Well, if you guys are trying to calculate those two, then you would probably have to look up the heat of formation values as well as the entropy of formation for those specific substances. And so you guys will have, in your Canvas folder, a reference sheet, if you will, that lists most, it's not all, it's a very, very short list of entropy, Gibbs free energy, and enthalpy values. And so if I just gave you a question like this, then that should prompt you to refer to that reference sheet. And you guys need to look up the standard entropy values and the standard enthalpy values of formation from that chart. And that's where you guys are going to get, that's where you guys are going to get your numbers. Now, to figure out the change in your standard free energy, standard entropy, I apologize, you guys are going to apply a version of Hess's Law where the change in standard entropy is equal to this whole stuff. Okay. And we did a few examples of that in a previous lecture video. Actually, we already calculated this in a previous lecture video, and the final answer was 180.16 joules per Kelvin. And so you guys would look up these substances in that reference sheet for the heat of formation values, standard heat of formation values. And so it turns out that there's only, two substances that's on that list. And I think I wrote it in the wrong place. Oops, there you go. And so here in this case, aluminum oxide is going to be negative 1,669.8 kilojoules per mole. So that's the heat of formation for aluminum oxide. And that of water in its gaseous state is going to be negative 241.8 kilojoules per mole. Once again, I'm grabbing all of these numbers from the reference sheet that's found in your Canvas folder for this specific chapter. Now, if you guys are looking at aluminum and hydrogen gas, which is found in your chemical equation, notice that there's no values listed down. The reason why is because these are pure substances, pure metallic substances, and the other one is a naturally occurring diatomic gas. So therefore, its value is going to be 0 kilojoules per mole. And so now that you guys have that information, by looking up the values in your reference sheet, you guys are just going to apply Hess's law for the heat of formation to determine the heat of the reaction. And the heat of reaction is going to give us the enthalpy value that we need to plug it into the overall equation, which is delta G, change in enthalpy, minus T delta S. All right. And so here it's telling us that we need to multiply the heat of formation by the coefficient, and the coefficient will have mole units. And so here we will have 1 aluminum oxide and 3 water molecules. So these 3 water molecules in gas state, I'm just going to erase this, is going to be negative 241.8. So that's going to be our product. So we only have one product in this scenario, which is going to be negative, I already forgot it. Oh, it's right there. So 3 times, so 3 moles times this by negative 241.8 kilojoules per mole. And that's the only product that I have that would produce some type of value. And so yes, aluminum is a product as well, but 2 times 0 is 0. So there's no point for me to include it in my equation. And so for my reactants, I have aluminum oxide and I have a diatomic gas. And so I'm just going to exclude the diatomic gas and the hydrogen in my calculation for enthalpy. And so here I have only 1 mole of aluminum oxide, and I'm going to go ahead and multiply that value by negative 1,669.8 kilojoules per mole. And so once again, I'm just going to go ahead and cancel out the unit for moles, and I'm going to multiply and subtract, and that'll give me my enthalpy value under standard conditions. And so here I have 3 times negative 241.8 minus negative 1669. So it's plus 1669.8. And so my change in enthalpy under standard conditions is 944.4. This is going to be kilojoules. Is that right? I think so. Yeah, it is. All right, so I was just making sure that I added my negative sign here, and I did. All right, so now that we have the value for the change in enthalpy, we're going to take that 944.4, and I'm going to go ahead and take this 180.16 and put it into this equation to determine the change in Gibbs free energy under standard conditions. And so here I have delta G is equal to delta H minus T delta S. So this value is going to be 944.4 kilojoules minus temperature, which is 298.15 Kelvin, and then entropy, okay, so that's a multiplication, it's going to be 180.16 joules per Kelvin. All right, so looking at our units, notice that we have a discrepancy. So you can convert kilojoules into joules, or you can convert joules to kilojoules. It doesn't really matter which one, just make sure that they're both the same units. I'm just going to go ahead and convert kilojoules to joules. So I'm just going to multiply this by 10 times 10 to the positive 3. Now, if you guys wanted to divide this by 1,000, that'll give you kilojoules. All right, and so I'm just going to go ahead and plug everything to my calculator. Here I have 944.4 times this by times 10 to the positive 3 minus 298.15 times this by 180.16. All right, so I'm going to go ahead and cancel these two out. When I multiply them, those Kelvin units cancel. And what I get is 8.907 times 10 to the positive 5. Okay. All right. And so final unit is going to be joules, and that's it. All right. So if I wanted to convert this into kilojoules, I can go ahead and do so. By taking out a times 10 to the positive 3. And if I wanted to expand this, it'll be 890.7 kilojoules. All right. And so now I've figured out the value of my standard Gibbs free energy. But if you guys look at the sign for this value, the sign is positive, right? I don't see a negative. And so this is telling you that the forward reaction is not, it's not spontaneous. Whereas if you guys were to compare the answer here, it's negative. So if your answer is negative, then it is spontaneous in the forward direction. All right. And so at this temperature, let's just kind of think about this real quick. Let's look at the signs. So notice our sign is positive for entropy and positive for enthalpy. And so if our sign is positive for enthalpy and positive for entropy, for this reaction to be spontaneous in the forward direction, the temperature must be much, much higher than 25 degrees Celsius. So temperature must be far, far greater than 25 degrees Celsius for the forward reaction to become spontaneous. So keep in mind that temperature is a source of a negative value. So if we can increase that negative value, then we're more likely going to get a negative answer for delta G, meaning that the reaction is going to be spontaneous. All right. And so we're going to go ahead and do one more problem here. So we're going to calculate the standard free energy change for the following reaction using standard Gibbs free energy of formation. And so here we're going to go ahead and calculate the same thing. Sorry, we're going to go ahead and calculate the standard Gibbs free energy of this reaction, but we're going to do it using the Gibbs free energy of formation rather than enthalpy and entropy and all that stuff. And so if you guys were to look at the reference sheet, then you can go ahead and look up the Gibbs free energy of formation values. And so for aluminum oxide, it's going to be 1,576.4 kilojoules per mole. For, once again, I think I've placed it in the wrong place. So for water, it's going to be negative 228.6 kilojoules per mole. And so if you guys were to look up the Gibbs free energy of formation for aluminum and hydrogen gas, it would be 0 and 0. Because these two are pure substances, and there's no point for us to make a pure substance if it's naturally occurring. And so all we're going to do is apply the modified version of Hess's law. So I'm just going to go ahead and copy and paste an equation here so I don't have to write it down. Where are you? Right here. And so we're going to use this equation to calculate the standard free energy change. Once again, standard free energy change is representing delta G naught, right? The standard is this little circle. And so if we have this equation to fall upon, the only products that we have that would make an actual difference in value would be that of water. Right? So if you guys look at aluminum, aluminum has 0 value. So 0 times 2 is going to be 0. And so what we're going to do is we're going to take 3 and multiply that by the value of water. So let's see here, 3 times 3 moles times that by negative 228.6 kilojoules per mole minus, and so hydrogen gas, that's a pure element, so we're not going to take that into consideration for our calculations for the reactants, and so we only have 1 mole of aluminum oxide, and so we're going to take 1 mole and multiply that by the value for aluminum oxide, which is 1,576.4 kilojoules per mole. All right, so the moles will cancel. And all you have to do is just plug everything in the calculator. Please don't forget the second negative sign. I'm not too sure why, but a lot of students somehow forget that when they perform it in their calculator, and they'll get an answer, excuse me, that is wrong. So it's going to be 3 times negative 228.6 minus parentheses negative 1576.4. And the answer that I'm going to get is 890.6 kilojoules. Okay. And so this technique is a lot easier and it's a lot more simple compared to what we did in the prior example. But the reason why I did this is I want to compare the actual answers. So example number 2 and example number 3, we're using the same chemical equation. The only difference is the technique that we're using. In example number 3, we're using the standard Gibbs free energy of formation, which is the equation that you guys see on the screen. Whereas in example number 2, we're using the definition of Gibbs free energy, which is delta G is equal to delta H minus T delta S. And so the main point for me to show you both techniques is to compare the final answer. And so this was the final answer for question number 3, using the second equation to calculate the change in Gibbs free energy under standard conditions. Whereas this is the final answer for this technique in which we used delta H minus T delta S. And so if you look at them, they're not exactly the same, but they're very, very, very similar. And so the main point that I want to convey is that, if you have the opportunity to apply whichever technique, I would definitely do the technique shown in number 3 versus number 2, just because it's a lot shorter and it's a lot faster. However, there are some scenarios, there are some questions in which you guys must calculate enthalpy and you must calculate entropy for whatever reason. But if you have the opportunity, feel free to take the quote-unquote easy route. It'll give you the same exact answer, same exact magnitude. The only way that you guys would get this wrong is if you guys executed it incorrectly in your calculation or in your setup. All right. So after going through those 2 techniques, that's pretty much it for this lecture video. In the next lecture video, we are going to explore the Gibbs free energy when it's at equilibrium. All right. I'll see you guys in the next video.